Oh, I hear you, girl. What you babbling about? Hello, everyone. Sorry it took me so long to get here. Computer difficulties. Computer that runs slow, everything's a drag. So it's like you go to click on something and it's moved by the time you click on it. So you click on something else and then you're somewhere else, and just not good. Well, we're just about finished with the course. Of course, I think what's it, May 2nd, I think is the last day of classes. Your final, of course, will be a final that's online that you do on a particular day. Put that on our syllabus. I can't remember what day it is right now, but that'll be the day that you have to do it. And you do it during our normal class time. If I remember correctly, it was we meet on Mondays and Wednesdays. So it'd be the last Monday of April. I believe that's what I decided on. If someone has a big problem with that, we could in principle do it on the last Wednesday of April, or we could do it on that second, which I think is a Monday. That's another option. But anyway, we're finishing tonight. We'll finish chapter 20. After that, I'm going into 37, 38, and 39, which are chapters on quantum mechanics. And I haven't decided what I'm going to do. I might just have you watch the videos where I introduce quantum mechanics and then just solve some problems like you're expected to be able to solve for the actual meetings. I'm not sure yet what's going to go along with that, but we'll find out first thing Monday. Well, when class starts Monday, not first thing. It is now 1 minute past time for class to start. Does anyone have any questions for me? Any questions? I read that once. I think it's questiones is the pronunciation of questions in plural in Spanish. I'm horrible with languages.
I thought it was preguntas. Was questions?
Is it? Yeah, it doesn't look like anybody has any questions. I'm hoping I'm laughing because you said it was something that I thought was funny, but I might have completely misheard you and laughing inappropriately, like Dr. Hibbert on The Simpsons. But that's another real possibility. Yesterday I had a doctor's appointment and asked them if masks were required, or do I just need to refrain from licking windows and door handles. And they said, yeah, no mask, but yeah, I would refrain from licking door handles and windows. I don't know where this line of jokes is coming from, but I've been doing it ever since COVID. I just act like I like everything. So as soon as I go to hand somebody my credit card, I act like I lick it and I hand it to them. But I guess it's not whether they think it's funny, it's whether I think it's funny. Oh, and by the way, check out my shirt. Monday's got me like, I'm just got a sloth laying there. That's awesome. Isn't that great? This is because I've decided that days of the week is an arbitrary construct created by human beings, and I'm no longer required to live by such a paradigm as Monday to Sunday. I'm just gonna live whatever day it is, and I'm gonna wear whatever shirt I want to do. Because I got like 4 really good Monday shirts, and I'm sick of not being able to wear them till Monday. So I'm gonna wear my Monday shirts any day I want to. And this doesn't technically have to say it's Monday, but anyways. So it looks like no one has any questions. Oh, so what I was telling everybody is Pearson's been down all day. I don't know what's going on with that. I don't know what the homeworks are set to. I got an email from one of my students saying he's having problems with the homework. I think it's because Pearson was down, but he might have actually had a problem with a date that was set before the thing was down, in which case, because he's a 242 student as well, in which case there might be something wrong with one of my due dates. So I will check that as soon as Pearson's back up. But what I did do is I went ahead and released, I think, our last 2 tests, which are 17, 18, 19, 20, or is it? Yeah, I think it's 17, 18, 19, and 20. And then the next one isn't actually released. It's going to release on, I want to say, the 20th. But that's on chapters 20 or 37, 38, 39. And 40, maybe something like that. I think it's 27, 37, 38, and 39. I think that's all. But that's the quantum mechanics chapter. So I just want to let you guys know those practice tests are up. Those tests are up. They have due dates. The due dates are firm because we're so close to the end of the semester. I can't help you guys anymore. I did change a particular due date on one particular test, but I don't even remember if that was this class or not, because I did all 3 of the classes. So just make sure you guys go and look at the Canvas and look for due dates. That I definitely didn't make anything due earlier than you expected. I just, set things which you might not have even seen existed yet. So in that sense, you might be surprised, like, oh crap, I've got something such and such due, because you didn't know the thing even existed. But other than that, you shouldn't be surprised as finding, well, this assignment I had written down in my calendar wasn't supposed to be due until such and such a date. Now it's due on such and such a date. That shouldn't happen. So hopefully I'm right. If I'm not, tell me which one it is exactly, and I'll correct it, because I didn't mean to do that. So when we last spoke, we were finishing chapter 19. And the big thing with chapter 19 is I got you some results for adiabatic processes with ideal gas laws. And that's actually something we're going to make use of today regarding the second law of thermodynamics. You'll see in our book, it actually states, I think, four or five different versions of the second law of thermodynamics. In this case, I expect you to know, of course, all of those laws of thermodynamics, and you'll see them as we go along. For instance, the Clausius version, or one of the versions, is that basically heat on its own will spontaneously flow from a warm body to a cold body, not the other way around. That is sort of one of the first ones we found. And that's sort of speaks to a deeper question. So there's all these problems in the world that in principle, according to the first law of thermodynamics and the zeroth law of thermodynamics, they could happen, no problem whatsoever. I mean, there is a scenario in which a puddle of hot coffee could suck the energy out of itself that it gained, that it had already, because it's, hot coffee, and from the floor, and suck all that energy out. The floor could transfer its energy somewhat to the coffee. The coffee could take some of its energy that's in the form of heat and spontaneously jump off the ground and form itself into the shape of a cylindrical volume, while bits and pieces of, say, ceramic or whatever, pottery, could spontaneously take their internal energies and the internal energy of the ground and convert them to kinetic energy and potential energy and shoot themselves off of the ground, all in such a way that they form a nice cylindrical cup with a handle on it around the cylindrical volume of coffee, and still have enough energy left over to rise up and land on top of a table. All of that's perfectly reasonable by the first law of thermodynamics, right? It's just a conservation of energy thing. You could literally do that. So you're stealing, the average random kinetic energy of the molecules and atoms in the actual coffee, in the ground or floor, wherever it was sitting. You're stealing it from the ceramic or whatever, porcelain or whatever you're using for the actual pottery and all that stuff. But there's no laws that say you can't do anything like that. So, I mean, as long as we just got the first law. So all these things could just happen at the same time. All these bits and pieces could jump together and form a nice cup of coffee, perhaps in a just an appropriate angle, maybe upside down or something, and fly all the way up onto the table, which you recognize is exactly the opposite of maybe me walking by and accidentally knocking over a cup of coffee onto the ground and our floor and it shattering and making a holy mess, right? So that's a neat topic. That's a whole different thing, though. In fact, it gives us an idea that conservation of energy is not enough. We need something more. We need something that can handle, while we never see that occur, but we frequently see, like I saw this Sunday morning when I walked out to my living room and dropped a hot cup of black coffee on my carpet, which is now the grossest, ugliest hodgepodge of colors of carpet ever, as I was convinced I could fix it by buying an expensive wet dry vac, using vinegar and dish detergent and water, boiling water, and then ultimately trying the experiment of all experiments, which is really, really dilute amount of chlorine bleach. Now I have a blondish carpet. It looks horrible. So, anyways, so yeah, that's something that can't happen. Well, it turns out that other thing that we need, when you look at it, you'll realize that that's the reason that you can look sometimes at a video. Often you'll see black and white video footage or something like that, and you can tell it's being run backwards. And the reason you can tell it's being run backwards is because you have an innate understanding that certain things happen. Coffee mugs do not assemble themselves around volumes of coffee and jump up onto tables. So if you saw something like that occur in a video, you say, oh, the video is running backwards, right? So we've actually given this something called times arrow. And it turns out that is another version of the second law of thermodynamics, is that times arrow is really a concept of the second law of thermodynamics, which says that basically in all processes, entropy, the total entropy of the universe, either increases or stays exactly the same. And it only stays exactly the same in processes we call reversible. And reversible processes are really impossible processes. They're sort of quasi-static, which I talked about in chapter 19, but they're even more than quasi-static in that they have to happen infinitely slow, and they're a series of equilibrium points from one spot to another, but infinitesimally far from each other, and have to go infinitely slow. If you can come up with that kind of process, which you can't, it's just not possible. But if you could, that would be a reversible process. Okay, so in a reversible process, the total entropy of the universe is going to, in fact, stay the same. In a non-reversible process, in other words, in all processes, the total entropy of the universe will increase. And you can usually say, in general, the entropy of the system is going to increase, but there's sometimes where you can actually make the entropy of a system decrease, and but the net effect for the whole universe is, in fact, an entropy increase. So then it's still okay. For instance, it's often been used by certain groups to suggest that the second law of thermodynamics is violated by the concept of evolution, biological evolution. That's not true. Okay, you can create order from disorder. It just takes energy, right? In other words, you've got to have more disorder occur outside of the system. If you consider the system the collection of cells that went from a hodgepodge of cells doing random things in random directions, you can take that same collection of cells and make them do very uniform motion that's very, very helpful and distinctive and ordered, just as long as more of the other cells or atoms or molecules in the universe are doing even worse. Okay, in other words, they're doing way more disordered things than the other things that have done ordered from its disordered state. And that's exactly how it happens. If we did not have a sun, for instance, to provide the energy, then yeah, we couldn't have had evolution. But we had the sun that could provide energy that could allow certain things to accumulate enough energy to become in a highly ordered state, which is another word for sort of anti-entropy is ordered and entropy is disordered. So you could have energy source coming in that actually makes things decrease in entropy, and that happens all the time. And that decrease in entropy just has to be matched by bigger increase in entropy somewhere else in the universe. So that's all it takes. Okay. So that's really where we're going today, as we're covering the laws of thermodynamics. I'm telling you the low-hanging fruit, the bare minimum I would expect as you, a student of chapter 20, is Mr. Younger expects me to know all of the versions of the second law of thermodynamics that the textbook gives me and their names. Okay, like the Clausius or the Kelvin Plunk versions of the second law of thermodynamics, and you'll see them as we go in our book. And they're bold prints, so not hard to write. So just take and memorize them, write them down, rewrite them down, rewrite them down, rewrite them down, and you'll have them memorized pretty well. Okay, find some mnemonic or whatever you want. All right, so the second law of thermodynamics, as I said, that really is a way of giving us, in some sense, times arrow. One of the main versions of the second law of thermodynamics, and I'm going to go ahead and read it to you in the wording of our book, because it tells you, where's that at, right? I thought they gave us that. Yeah, they gave us it first, just the Clausius statement, and that's named after R.J.E. Clausius, who lived from 1822 to 1888. I really like it when I see people's years, dates, all sorts of cool stuff as multiples of 11, because that's really fun. But anyways, 1822 to 1888 is when he lives, and it says heat can flow spontaneously from a hot object to a cold object, semicolon. Heat will not flow spontaneously from a cold object to a hot object. Okay, that's the second law of thermodynamics in the Clausius statement. So the Clausius statement of the second law of thermodynamics is heat flows spontaneously. Spontaneously just means on its own. You don't have to do anything extra. We can make heat flow. For instance, I'm looking at my fridge. Well, I'm pretending to look at my refrigerator. It's just a stupid wall in the way. It won't let me see my refrigerator. But anyways, the refrigerator in my house literally is a device that takes heat from the cold inside the refrigerator and blows it out to the hot of the kitchen in which it's located. Okay. Yes, we can do that, but that's not spontaneous. That, in fact, is the very opposite of spontaneous. That is costing me money, because the power company sends me a little bill every month that says, hey, here's all the money you've been wasting by cooling off your mayonnaise to keep you from getting deathly ill from eating hot mayonnaise sandwiches. Okay. So, yeah, I said sandwiches. But anyways, so it doesn't say that heat can't flow from a cold object to a hot object. It just means it's not going to do it on its own. So here's a neat process you can imagine. It's actually very simple, because we'll ultimately learn that this entropy thing that I told you about, one version of it is the amount of heat, Q, divided by the temperature. And if the temperature stays constant, then you just use that temperature. If the temperature changes by just a little bit, maybe you use the average temperature, and that'll be fine. So here's a neat problem. You can imagine that I take, say, let's say a 20-gram block of aluminum, heat it up to 100 degrees Celsius, and I stick that in, let's say, of 70 grams of water at 20 degrees Celsius. So 100 degrees, 20 grams, 20 degrees Celsius, 50 grams. Okay. I stick that in there. I allow it to reach equilibrium. You know what's going to happen. The 100 degree, 20 gram hunk of aluminum is going to lose heat and heat up the water. And hopefully you know enough about specific heats to tell me this answer. Can somebody tell me? So the water was initially at 20, the metal was initially at 100, the water's 50 grams, the metal is 20 grams. Do you think the final temperature will be smaller than 20? Do you think it'll be bigger than 20 but close to 20? So that's number 2. Or do you think it will be midway between 20 and 100? That's number 3. Or do you think it will be close to 100? That's the 4th answer. Or the 5th answer, do you think it'll be greater than 100? So your choices are below 20, above 20 but really close to it, dead center between 20 and 100, below 100 but really close to it, or greater than 100. Again, that was a 20 gram hunk of aluminum at 100 degrees Celsius put into a 50 gram container of water at 20 degrees Celsius. Anybody want to chat a guess at that?
I feel like it'd be closer to 20, like it'd be greater than 20, but closer to 20, because the specific heat of water is going to absorb more energy than the aluminum.
Excellent. Yes, that's exactly the correct reasoning, and that's exactly the right answer. In fact, we often do that as one of our experiments. I don't think we got to do that with you guys online, since you guys are online this semester. But yeah, we literally do an experiment like that, and we, you know, it's hard to get the temperature of a metal, right? It's not like a baby or a human where you can just, you know, stick a thermometer in an orifice and wait for it to reach equilibrium. You can't do that with a chunk of metal. So what we do, and it's the same reason why we use this method in cooking, is we take the chunk of aluminum or whatever metal we're doing, and we put that in boiling water and leave it there for a long period of time. And since, you know, aluminum is a metal, it's a conductor, it should reach equilibrium with the water pretty quickly. Leave it in there for 3 minutes. That's more than enough time. Then we drop it into the water, whose temperature we've measured just as we put it in there. And lo and behold, even if it's more like, you know, 50 grams of aluminum and 50 grams of water, it's still only going to change to about 22 degrees Celsius. Because like you said, the specific heat of water is 1 calorie per gram Celsius degree, whereas like the specific heat of aluminum, if I remember correctly, is like 0.22. So it's literally, you know, almost 5 times smaller than the specific heat of water. So good job with that one. But here's a neat thing. We can say, okay, well, we know what's going to happen. It's going to reach equilibrium, and that equilibrium is going to be around 22 degrees Celsius, say. Let's just assume that's the case. You can now, you know, do the calculation, figure out what that temperature would actually be. It probably, like I said, probably be around 22 degrees Celsius. Just by the thermodynamics, the calorimetry stuff I taught you, you can actually do that. Again, taking the problem being 20 grams of aluminum and 50 grams of water, aluminum at 100 degrees, water at 20 degrees Celsius. Just count those two is all you need to count. And what I want you to do is calculate the energy loss from the aluminum and the energy gain from the water. And of course, set those equal to each other. That'll give you the temperature. Now I want you to say, okay, let's imagine instead that the water was 22 degrees Celsius, as was the aluminum, and spontaneously the water switched to 20 degrees Celsius, and I'm saying 22, assuming that was the answer you got in the other problem, but whatever answer you got in the other problem is what you're going to use. assume that the water gained enough energy, or excuse me, lost enough energy to lower its temperature to 20 degrees Celsius, and that the aluminum gained enough energy to go back to 100 degrees Celsius, and see if that doesn't give you exactly the same calorimetry. In other words, the calories lost by the water is exactly equal to the calorie gained by the aluminum. So that shows you definitively that conservation of energy doesn't prevent that from happening. So that's a wonderful, excellent little example for you guys to try. It's on videotape now. I've explained it pretty well, multiple times, in fact, so y'all can do that as an extra credit and turn that in. Now, the big deal is what will change is entropy. So you can calculate the entropy, which is the heat. Let's say the heat added to the water would have been a positive Q, and then you divide that by temperature. Since it went from 20 to 22 or whatever you calculated it was, take the average if you want, that'd be fine. And then do the same thing with the heat gain, the heat loss, which would be negative for the metal, and divide it by the average temperature, which again is taking a big assumption there, the average temperature of the aluminum. And you'll find out that, in fact, when you do the other way around, you'll get a decrease in entropy instead of an increase in entropy. So that's a neat little thing you can try, but it's the one law that tells us that that doesn't happen. We don't spontaneously have hot objects absorbing heat from cold objects to get hotter. Okay. Now, that was the first version of the second law of thermodynamics. The second version is going to require a heat engine, and heat engine is basically like a steam turbine. That's a version of a heat engine. Steam turbine is, in fact, basically what we use to generate power. If we've got a nuclear power plant, if we've got a hydroelectric power plant, if we've got a coal-fired power plant or a oil-fired power plant, any of those types of power plants, just about, we're all going to use a steam turbine heat engine. And basically what it does, and your book has two versions of a steam engine that it shows you, but basically what's happening is you take something, the working fluid, and you heat that up some way. So if it's a nuclear power plant, what you're basically allowing to occur is uranium-239 is going to decay to uranium-235 and give off a bunch of alpha particles. And those alpha particles are going to bombard a lot of other things. It's going to heat all of them up, and that's going to cause the water to come to a boil. And that boiling water will then run by some blades in a turbine, and those blades are going to spin, and that actually is a form of work. You've got, work equals force times distance, or the integral of F dot dl, but you've also got work equals the integral of torque dot d theta. So that's another version. So you can get work out that way. And then as that steam drops its energy onto those blades, it cools off and condenses it back out into a liquid form, and is then fed back into the system where more uranium reactions, in this case it's actually fission, not fusion. Fission's what goes on in the sun, or excuse me, fusion's what goes on in the sun, fission's what goes on in nuclear power plants. That reaction continues to take place, heating up water again, turning it to steam, and then the steam goes back, and so on and so forth. But you can see the water's really innocuous. I mean, unless you've got a leak or something, the water's not anything that could harm you. If you've got some leak somewhere in the system, then yeah, maybe it's going to actually get some radioactivity in it, and that would be a problem. But it can hurt, for instance, to heat up a nearby lake, because they'll have cooling towers like you've seen on The Simpsons, the hyperbolic shaped cooling towers, and they'll normally have a nearby lake. And if that lake is actually a natural lake with fish and stuff in it, you could actually cause a lot of eco problems with regards to fish and plant life and stuff like that. You actually introduce a system that it wasn't meant to be there and didn't have enough time to evolve to adapt to that system. So that can cause other problems. But generally speaking, the water's fairly innocuous. It's just water that's been heated. Okay. So that's what a version of a steam engine is. In that case, it's a steam turbine. But in general, what we look at it for a heat engine is something that takes heat from some hot reservoir. And like I told you before, when you say a reservoir, you really mean something that it can steal heat from it and you really don't change its temperature. So I could steal heat, probably all day long from a 2,000 acre lake in the Ozarks, no problem, because it's not going to change the temperature. So the 2,000 acre lake in the Ozarks is a heat reservoir. That would be fine. A heat engine takes that heat and then uses as much of it as it can to create work. That work could be expanding a piston. It could be expanding a piston that has a piston rod on it that turns a camshaft or a crankshaft, excuse me, and that could actually rotate a transmission, and that rotating transmission could, of course, go into a differential or into a transmission, another part of a transmission with another part of wheels, so it can spin at a different rate. That could go into a differential and then rotate a tire, so on and so forth. So that's the work part. But it turns out, once you take that heat, that Q coming out of the reservoir, and convert some fraction of it to work, it turns out there's going to be some fraction, no matter what you do, some fraction is going to be lost to another reservoir, which is the environment. Okay, no ifs, ands, or buts about it. And in fact, that's another version of the second law of thermodynamics. So let me find that version real quick in your book and read that to you. They say it two different ways in this thing, and one of them is just like a parenthetical. So it says, no device is possible. This is called the Kelvin Plunk statement. No device is possible whose sole effect is to transform a given amount of heat completely into work. So what I'm saying is, if you're pulling heat out of a reservoir, I said you're going to take some fraction of that and convert it to work. And that fraction is not one. Okay, that's what that says, but it gives you a second statement. So hold on first. It says, no device is possible whose sole effect is to transform a given amount of heat completely into work. That's the Kelvin Plunk statement of the second law of thermodynamics. But then down here it says, there can be no perfect 100% efficient heat engine, which means basically there's no way you can get 100% of the energy that comes out through the heat coming in to be work. Okay, so let's start by talking about a specific heat engine, but first by talking about the efficiency of a heat engine. So let me turn on my document cam. The efficiency, which we'll use a lowercase e for, the efficiency of any device is what you get divided by what you pay for. What you get, well, let me put a space between you and get, because I'm going to pretend we're using the modern version of English, not something some cannibal wrote. What you get, and I'll put and actually wanted. Okay, because you're going to get that heat out too, whether you want it or not. So I don't want you to think you can count that. So what you get divided by what you pay for. So a classic diagram of a heat engine is, here's a heat reservoir whose temperature is TH. Here's an engine, if you will, and this engine's kind of weird, but this engine is going to put out work, and it's going to be a heat engine. And what's going to happen is, flowing from this hot reservoir is a certain amount of heat, QH. Okay, completely throwing away all the sign conventions right now. We're just saying, hey, QH is coming in. Okay, now this heat engine is also spitting out, and the circle sort of represents the heat engine. The heat engine spitting out some work, again, ignoring all sign conventions. And then what's left is being delivered into this other heat reservoir, which has a temperature T low, or T sub L, and the heat delivered there is Q sub L. Okay, so that's the classic picture of a physics heat engine. Obviously, that doesn't look anything like an engine, doesn't look like a car engine. A car engine, by the way, is a heat engine. A steam engine is a heat engine. Steam turbine's a heat engine. The two-stage thing they talked about in your book is a heat engine. But let me show you what they mean by this as far as the efficiency goes. So what you want, what you actually want and what you get is the work. So that's the top. But what you pay for is all the crap you put in, and that's the QH. So that's how much energy you put in. Notice all of that didn't go into the work. Otherwise, you'd have a 100% efficient engine. Some of it's got to be wasted. Another version, and I'm not going to test you on this one, but a version that I use for my conceptual physics classes when I teach those for the second law of thermodynamics is that there's different types of energy. Heat energy, there's internal energy, which is again another type of heat. There's kinetic energy, there's potential energy, there's nuclear energy, there's binding energy. All of those different types of energy are all different types of energy, and they can exchange back and forth all day long, no problems. The problem is there's a bastardized version of energy, and that version of energy is called heat. Once any type of energy is converted to heat, you're never going to get it all back. It's a low quality energy. So that's another way of thinking about the second law of thermodynamics, is that heat is a low quality energy. Therefore, you're never going to get all that you put in back. And then that means this is never going to be just an empty pipe. This pipe is always going to have some heat flowing to it. So that's really what a heat engine is in general, is something that takes in a certain amount of heat, it puts out a certain amount of work, and it has to expel a certain amount of exhaust heat as well. The efficiency, of course, is W over QH. Of course, QH is also equal to W plus QL. So you could do that, and then you could say it's 1 plus Q 1 plus Q over QL or something like that. You can actually you can change the W into, since QH is equal to W plus QL, you can say that W is equal to QH minus QL. And then you can see that you'd have QH over W minus QL, QH minus QL over W plus QL. And that would be 1 minus QL over QH, excuse me. It don't matter which order I put the denominator in. So that's another way of writing the efficiency. And that's absolutely right. It's just we're going to find another way to do it for a very specific type of heat engine. You will learn there are several types of heat engines that have been thought up. One's a Stirling engine. One's a Carnot engine. That's the one we're getting ready to study. And the one closest to the automobile is the Otto engine. Sorry, that was my rough impression of Long Duck Dong from 16 Candles. Anyways, Otto, not to be related to AUTO, but that's 3 of the types of engines. The Carnot engine is kind of neat, and I'm going to show you what that is. So let's work on Ely, that's his name, Carnot's engine. The Ely Carnot engine is a pretty straightforward process. We're going to look at a pressure versus volume diagram. Okay. And in the Carnot engine, basically what happens is we're going to use this thing that I talked about already. We talked about a reversible engine, and I told you how reversible is like even bigger deal than quasi-static. But what I'm saying here is we're going to have one of those engines, and it's going to be some other special things. So first off, we're going to have an isothermal process. So I'm going to go from point A right here along an isotherm. So point B. So in other words, this line right here is TH equals a constant. Okay, in other words, we're also going to use an ideal gas, and for an ideal gas, we know PV equals nRT. So if T is a constant, then P is just some number over V. So this is like a hyperbola. So that's why it has that specific shape. And that process is isothermal. So this one right here, since it's at a constant temperature, that means it's isothermal. It's also all reversible. So all reversible. And by the way, when it says reversible, that means every state is in fact an equilibrium state. That's why you can graph it. If it wasn't reversible, you couldn't actually graph it because the pressure and volume don't really have a value except in equilibrium state. So it's all reversible. It's an ideal gas. Is involved as well. Now the second step is going to go from B to C. Notice I actually took in a certain amount of heat right here, and that amount of heat is going to be QH. So that corresponds to that heat coming in there. The next step is in fact going to be an adiabatic process. And notice the volume increased again from B to C, and this is in fact an adiabat. Adiabatic process. So no heat ran in there. It was just an expansion. So what you can imagine is this is, you can sort of think of it as like a heat engine or like a car engine. So for instance, when the fuel air mixture comes in to the chamber of the piston, that is partly comes in by the valves allowing the gas to enter, but also by the volume that the piston is making out of the cylinder is increasing, and then there's an explosion occurs. You can sort of think of this as like the explosion that occurs. That explosion is going to deliver a buttload of heat, like bam, really fast, right? At that point, that heat can't really go anywhere, but it's going to cause the cylinder, the piston, to move even more to make the cylinder even larger volume. So that's what just happened there. But in doing so, the gas is cooled down, because when you expand a gas, it cools down. So now we're on, in fact, a separate isotherm, and this is T low, which is a constant. And this time it's going to come up like this. And that's going to go from C to D. And that part, of course, is isothermal. Now notice what's happening. The volume's actually shrinking. So what's happening is now the intake valve has opened up, and it's allowing that cooler gas to escape with the amount of heat QL. Okay. And then there's another adiabat that goes from D to A. That's the Carnot cycle. Okay, so there's an adiabatic process. Now, we're only concerned with heat engines that are cyclic. In other words, that start and stop at the same place, because when they start and stop at the same place, we know the internal energy, which is a state variable, can only depend on the initial and final state. So the total internal energy change from here to here is 0. So one cycle implies delta E internal is equal to 0. Okay. And as we learned before, the area inside this curve is really the work done. So if we can calculate the area inside that curve, then we'll actually have the work done. But I'm going to do even more than that. What I'm going to do is I'm going to be able to show you that, in fact, the Carnot engine, its efficiency can be reduced down to just knowing the temperature of the two isotherms. So first off, when I do the work from A to B, that's the integral of P dV. Okay. Well, that's an isotherm. So that has a constant temperature TH. So using the ideal gas law, because remember I said it's all reversible and it's all an ideal gas, I can say P is equal to nRT over V. So in this case, I get nRT hot times the integral dV over V, which is just, let's call it VA. VB minus VB is the final one and VA is the initial one. So the work done is in fact nRTH natural log VB over VA. Okay. Now, since it's an ideal gas, delta E internal is equal to, if it's monatomic, it'd be 3/2, but I'll just say F over 2 nRT. Right? That's what the internal energy is. Well, the internal energy didn't change. So actually, I should put delta T there. Sorry about that. nR times delta T. But delta T is equal to 0. So the second law of thermodynamics, which says delta E internal is equal to the work done, or excuse me, is equal to the heat added to the system minus the work done. You see that since this is 0, this work done has to be equal to QH. So now we say, oh, okay, well, evidently QH is nRTH natural log VB over VA. Does that make sense to everyone? Well, for the exact same reasoning, we can now say, oh, well, clearly the same thing's going to happen here. And I'm going to get Q low is equal to nRT low times the natural log. In this case, it'd be VD over VC. So we've got those two quantities, and that's all well and good. But the main thing is we can use the fact that it is an adiabatic process over here and here, because when we learn first from the ideal gas law, we know that P1 V1 over T1 is equal to P2 V2 over T2. That's for any ideal gas. So I'll just label that I period G period. But we also learn that for an adiabatic process, we learned that P times V to the gamma, so P1 V1 to the gamma power is equal to P2 V2 to the gamma power, where gamma was just supposed to be equal to CP over CV. Okay. So that's kind of nice, right? So I know from A to B, or from A to D, I should say. I know from A to D and A to B, I can relate these quantities using this. So for instance, B and C is related through an adiabat. I can say PB times VB to the gamma is equal to PC times VC to the gamma. That's one case. I also know that PD times VD to the gamma is equal to PA times VA to the gamma. But I also know that P, and again, we're just going to use the B's to the C's, PB, VB over TH. Well, actually, I don't want to use the TH yet. Sorry about that. Yeah, I guess I will. No. Yeah, PBVB over TH. That'll work. I'm just trying to remember when we're at state B, it clearly is at the temperature TH. So it's okay to put the TH with the PB and VB. I was getting confused for a second there because I was afraid I was going to have to use that with the C, but I don't have to use that with the C because the C has the other temperature, the TL. So that's equal to PC VC over TL. And similarly, I had to really pronounce that, didn't I? PD VD over, and again, that was TL, is equal to PA VA over TH, right? So now all I have to do is divide these two equations. Excuse me, divide these two equations by each other, and I'll get something kind of nice. So if I divide this equation by this equation, notice the TH comes up on top. I get TH, and then I get VB. Notice the PBs cancel out. I get VB to the gamma minus 1. And then on this side, I get TL on top, and then that's VC to the gamma minus 1. Similarly, over here, I get TL on top, VD to the gamma minus 1, and TH on top, VA to the gamma minus 1. So from this guy, I can see, because what I'm really trying to figure out is what are these things? What's like VB over VA? Well, I can see that VB over VA at least to the gamma minus 1 power. I just got a bad running nose all of a sudden. Okay, so VB over VA to the gamma minus 1 power. So if I solve this for VB, I would say VB to the gamma minus 1 is equal to TL over TH times VC to the gamma minus 1. Everybody sees that? Sorry, I had to fit it up in that little corner there. Now, if I did the same thing over here with VA, I would say that, okay, so VA to the gamma minus 1 would equal TL over TH times VD to the gamma minus 1. So if I write VB over VA, I'm just going to take this and divide it by that to the gamma minus 1. So I'm going to get TL over TH VC gamma minus 1 over TL over TH VD to the gamma minus 1. The TL over TH cancels out each other. So you see VB over VA to the gamma minus 1 is equal to VC over VD to the gamma minus 1. Now, why is that relevant? Well, that's relevant because it tells us that VC over VD and VB over VA are really, I think I might have got that in the upside down order, VC over VD and VA over, oh, yeah, I can still flip that over. I can say, I can flip this over and make it VA over VB. All right, I can flip this over and make it VC over VD. The main thing is, oh, I was supposed to do D to A, not D to, no, I was supposed to do D last and C at first and B last. Yeah, okay, that's all good. All right, so because of that, what I can see is that this efficiency term, the QL over QH, which would be this divided by that, the only thing that's left is TL over TH because these lens are going to be equal to each other because of this being equal to each other. Therefore, E becomes 1 minus TL over TH instead of just this simple expression. Okay. In other words, as I argued or as I advertised, for a Carnot engine, the efficiency only depends on the temperature of the cold reservoir and the temperature of the warm reservoir. And another version of the second law of thermodynamics is that basically no engine can ever be as efficient as a Carnot engine and are more efficient than a Carnot engine. And the only engine that can be as efficient as a Carnot engine is a reversible engine, which of course we've talked about reversible being impossible. So there's really no such thing as anything being as efficient as a Carnot engine. But you can use that as a standard if you want to, for instance, talk about, you know, how efficient is a car engine or how efficient is a steam turbine. Well, it turns out a car engine might get in the 30s or 40% efficiency, and I'm meaning 30 to 40% of what the Carnot efficiency would be, not 30 or 40% efficient. So whereas a steam turbine might get as much as 50 or even 60% of a Carnot engine. So that's really the whole crux of why I gave you that adiabatic stuff where the P times V to the gamma equals P times V to the gamma, all that good stuff. I see I got them in a sort of a reversed order, but it doesn't matter. The main thing is we were able to come up with this efficiency, and that's something you can use over and over. You'll see the examples are really, really simple for doing this. Now, that's the efficiency, for instance, for a heat engine. If you want to talk about something else that exists and is actually very helpful, it's not just a heat engine. Another thing that's valuable is, for instance, an air conditioner or a refrigerator. In those cases, you don't talk about the efficiency, you talk about the coefficient of performance. So for air conditioners, and refrigerators, I'm trying to look for the one It's really sad, but there was a brand of refrigerator a long time ago called a Frigidaire, and I cannot write the word frigid without thinking there's a D here. So refrigerator. That was the other thing I was doing, was double checking my spelling. So refrigerators and air conditioners, they actually have something else. They have COP, the coefficient of performance. And the coefficient of performance is called COP. You can look them up at Lowe's or Home Depot or whatever. But here's what's going on with regards to refrigerator or air conditioner. So again, you have a hot reservoir, which in the case of a refrigerator would be your kitchen, right? And then you have your refrigerator, which I draw as a square this time instead of the circle that I drew last time. And then you have a cold reservoir, which is the actual insides where you keep all the food and stuff. Okay, so that's T cold or T low. Yeah, I'll call that low since I called it the other one H. So what you're trying to do is you're trying to take heat out of, again, throwing away sign conventions and taking a heat QL out of a cold space. And of course, that's going to require some work that I'm going to put into it. So that work's actually going in this time instead of out. And then, of course, that's going to dump some of that heat outside or into, in the case of a refrigerator, into the kitchen. Okay, so literally your refrigerator is making your kitchen more hot, just like your light bulbs are making your house more hot during the summer. Okay. So that's really what's going on. And just like efficiency, it should be what you get divided by what you pay for. The coefficient of performance should be what you get divided by what you pay for. Well, what you're getting that you actually want is how much QL is coming out here. So the QL is the top. And then what you're putting into it, of course, is the W. So that's what the coefficient of performance is for a refrigerator or an air conditioner. Now with a heat pump, you just turn it around backwards. And what I mean by that is you literally would take and start running the stuff backwards. You would run the heat into the heat pump, only this time you're going to start taking cold air from the outside. You're going to start taking heat from the outside and pushing it into the warm house. Okay, so for a refrigerator, that's that. But for a heat pump, this is your house. So with a heat pump, which is what a lot of modern houses have nowadays, instead of a, gas packs, or instead of a wood fireplace or something like that, they'll have something called a heat pump. And a heat pump can run one way as an air conditioner, and it runs the other way as a heat pump. So when it's taking cold air out of your, when it's taking heat out of your cool house, it's running as an air conditioner. But when it's taking, of course, running backwards, taking heat out of the warm house and putting it into the outdoors, then you're running as a refrigerator, or as a air conditioner, that sort of thing. So anyways, that's just a brief intro to that. The problems that are associated with these types of equations, this efficiency and coefficient of performance, are really pretty straightforward. And again, I want you to do them for your homework, and I want you to do them for your practice tests. And then when you look at your tests, I want to make sure you guys just know your second law of thermodynamics, because I fairly often do not test much beyond that. Okay, maybe I'll ask you to calculate an efficiency, maybe I'll ask you to calculate a coefficient of performance, or maybe I'll ask you to do an example just like one of the examples in the book where they use COP or efficiency, but that's pretty much it as far as the whole test goes. We don't even cover second law of thermodynamics in most of our classes. Now, another version of the second law of thermodynamics is about entropy, and it turns out there's another state variable. So another state variable, and remember, state variables are ones that you can actually put a D in front of and say like DE internal, because there is a function E internal that's relating certain state variables together. And if you have to, for instance, integrate it, you can evaluate it at the two endpoints. That's a state variable. Not everything is a state variable. For instance, heat and work are not state variables. But there is another state variable. There's actually several of them that I'm introducing, and this one is called entropy. And one of the classic names that we call it in terms of layman's language is disorder. And you can, in a sort of waving of the hands way, you can sort of use it to understand things like why it's easier to pull out of a parking space than it is to pull into a parking space. So imagine this, just to give you a hand wavy idea of what I mean by that. So when you pull into a parking lot, you have line, 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 and your car comes in like this, right? Your car is smaller than the separation between these lines, but notice your car can pretty much fit. I'll show you the different ways. Let's assume we're going to this parking space. So we're going to this parking space right here. That means your car can park right up against this line. It can park a little bit further towards the other line, a little bit further towards the other line, and just a little bit further towards the other line. It can also park at a slight angle. I'm drawing an exaggerated angle here. It can park at a slight angle or a slight angle the other way. And then all those little angles between are acceptable as well, right? So you can see maybe you come up with, I don't know, around 25 possible positions that you can park. However, when you go to pull out of a parking space, out of that parking space, you can come out this way. You can come out from just to the side of it. You can come out from just to the side of that. All those ways we learned that you went in, you can come out, but you can also come out at a slightly different angle and a slightly different angle than that and a slightly different angle than that. So you can see there's like an infinity of possible ways to pull out. So a disorder is a measure of the number of ways something can be done, right? The more ways it can be done, the more disordered it is. So you're actually really increasing your entropy by pulling out of a parking spot, whereas you're really decreasing your entropy by pulling into a parking spot. So that's a way of thinking about it. But it turns out it is a state variable, so you can actually write it as ds. If you want to think of it as small changes, then you have to do this weird thing that I told you about before, where I put a little bar on the Q and then put it over T, and that is a definition of entropy. So the change in entropy is the amount of heat added divided by the temperature at which it occurs. Now, if you can find Q as a function of T for a particular, let's say, reversible process, then this DQ is perfectly allowed without the bar on it. And since this is a state variable, it's going to be true just as long as the initial and final states are the same. So you don't have to find reversible processes to make this work. But if you can calculate a reversible process that goes from A to B like your problem does, then that's still going to give you the right answer, even though the way it was done was entirely different, because this is a state variable and only depends on the initial and final states. So that is a version of entropy. Another version of entropy that's really nice, it turns out that S is actually equal to the Boltzmann constant. Remember, we learned about that earlier. The Boltzmann constant, I also called it K sub B, which turned out to be the ideal gas constant divided by Avogadro's number, which is 1.3807 times 10 to the negative 7th joules per Kelvin, I think. Well, that's another way you can actually define entropy. And well, you have to add something else to it, and I'm going to give you that in a second, but I want to make sure my value of K was right. It might help if I look on the right page, because clearly that doesn't matter. Value of K. Yeah. Oh, no. -7. No, that's not quite right. 10 to the negative 23rd. Joules per Kelvin. Okay, so yeah, that was the part I wanted to correct, and now I'm really glad I did, because I would have hated to have you go off thinking it was 10 to the negative 7th. So I'll rewrite this a little clearer, hopefully. Okay, well, the other version of entropy is K times the natural log of this fancy W, and this fancy W is actually something called the number of microstates. So W is the number of microstates corresponding a given macrostate. Now that's a lot of words that you've never heard before, microstate and macrostate, but imagine this way. Imagine you have, pretend like you have 100 balls, okay? And you have, let's say, and let's assume that we can actually tell them apart, for instance, that might help. And let's say we have like 5 shells, okay? And let's say we have 100 million joules of energy to distribute amongst them 100 balls, right? Well, what we might do is take all the blue balls and put them in this highest shelf, which is worth 1 million. Okay. And then we might take all the red balls and put it in this shelf, which is worth 1 times 10 to the 5th joules. And this will be 1 times 10 to the 4th. And this will be 1 times 10 to the 3rd. And this will be 1 times 10 to the 2nd. Now, if you can imagine, maybe there's red, blue, yellow, green. So maybe there's red, blue, yellow, green, white, and let's say orange balls, right? If you can imagine all the different ways you can pair these up such that all 100 balls are used and you've got 100 million joules, the number of ways you can do that is the number of microstates. And the macro state is the case of 100 balls with 100 million joules. Okay. So the entropy of this system would be, I'd have to count all the different ways. I'd have to first say, well, I got 100 balls and 1, 2, 3, 4, 5. I really wish I wouldn't have made that orange there. Let's pretend we don't have orange there. So let's say we have 20 of each. So now I just say, okay, well, how many ways can I put 20 red balls in all these different slots, and 20 blue balls in all these different slots, and 20 green balls and 20 white balls in all these different slots, such that the total amount of energy is 100,000. Once I count all those, I take the natural log of it and I multiply it by 1.3807 times 10 to the -23rd, and that gives me a measure of the entropy. Okay. And the fundamental law now that comes from all this is yet another version of the second law of thermodynamics, which I'm looking for right now. Must have been earlier. In any natural process, some energy becomes unavailable to do useful work. That's sort of like one we already did. Why aren't they doing it in terms of entropy? I thought they wrote it a separate place in terms of entropy. I know they did because they talked about it in the evolution section. I'm not seeing it now. Okay, here you go. Natural processes tend to move toward a state of greater disorder or greater entropy. Statement C is the most general statement of the second law of thermodynamics and can be restated as the total entropy S of any system plus that of its environment increases as a result of any natural process. So delta S is greater than 0 for a natural process. And of course, it can only be 0 for a reversible process. But that's another version of the second law. Your book says, and this is something that's kind of a thing that we don't really pay much attention to, but in reality, it turns out it's really, really, really hard. We seem to be able to get as close to 0 Kelvin as we want, but we can't reach 0 Kelvin. So that's now become the third law of thermodynamics. You can't reach 0 Kelvin. So that's another issue. Your book also talks about global warming. I want to give you, since you only got like 5 minutes, I'm going to go ahead and give you a little rundown on what global warming is and what it means when we say things like 99.9% of climatologists, the people that should know, agree that 1, the globe is warming, and 2, we are greatly responsible for that. In other words, yes, we're not the only thing responsible for it, but us humans have the lion's share, and I mean the real lion's share, like on the order of, there's some arguing to this, but maybe as low as 93%, but maybe as high as 97%, that sort of thing. Okay, so what global circulation models, that's what they really talk about. They're not global climate models, they're called global circulation models. And what they are is sort of like the models we use to model our sun. We have we divide our sun up into an inner core that has some small radius, and that's not necessarily the core of the sun. That just means the inner core of our model. And maybe that's 1/10 or 1/100th of the radius of the sun. And we imagine that as a little sphere. And then that sphere has a surface area, it has a temperature associated with it, it has a mass inside of it, it has a certain percentage of hydrogen, a certain percentage of helium, stuff like that. And then you go again another 100th of a radius out, and that's a little spherical shell that has an inner radius and an outer radius and all those same parameters, temperature, mass, all that good stuff. And then they set up all these differential equations that have to be true, like equilibrium must be established, all the force on the outside must be equilibrated by a force on the outside pushing out by radiation. If any energy leaves one of those little spherical shells, it has to either go out the surface below or the surface above. It can't just disappear, stuff like that. Well, we do the same thing with the atmosphere. So we imagine the Earth as if it's like a sphere. We know the Earth has a certain percentage that's water, and we know how water behaves, fresh water, salt water, with heat. We know how it behaves with sunlight. We know how it behaves with atmospheric pressure. We have a fraction of it that's sand due to deserts. We have a fraction of it that's greenery like rainforest. We have a fraction of it that's urban, all these different things, and we take all that into consideration, and then we divide the atmosphere up into these little layers, and then we just subdivide those little layers up into little rectangles or little squares, say, that might be 10 to 100 kilometers by 10 to 100 kilometers by, say, 100 meters thick. Again, we have all those same equations where the total mass of all the little parcels has to add up to be the total mass of the atmosphere. They have to obey the laws of physics. If heat flows in, it's got to flow from one side to the other. First law of thermodynamics has to be allowed, all that good stuff. They put all that junk together, and if you've ever coded before, it's a nightmare, because you make one little mistake, one little syntactical error, and you could literally just sit there and let it run for weeks and not know anything's wrong, right? And then it still never put out anything. But they eventually do that, and they get it to work, and they make it run through various tests, and tests like, does it obey conservation of energy? Does it obey conservation of mass? Does it have the right mass? Is the mass of the atmosphere accurate? And then this is the kicker, okay? Once they have that model, and it's based on, again, certain parameters that they're using, like percentages and stuff like that, once they have that model, they say, well, does that predict what we know already happened? In other words, if I take the data that I had in, let's say, 1925, I know the conditions pretty accurately on 1925 across the whole globe. If I put those into my model, is that going to tell me what the globe did from 1925 to, say, 1950, 1975, or even 2000? If it did, they pat themselves on the back, say good job, and then they go and look for another batch of years, and they see if that works. And then if it did, they pat themselves on the back. And only once it's done all that stuff, been through those tests of the laws of physics and tests of whether they predict what we already knew, only then are they really publishable or even usable. Okay, so the IPCC, the International Panel on Climate Change, is a collection of sort of the best from each country of the scientists of most countries, not all countries, but the best climatologists from each of the countries in the world put their person forward, and those people try to choose, using scientific methods, looking at the papers and the publications, try to choose on a yearly basis, mind you, the best models out of all those models that have been written. So they've got hundreds of thousands, if not millions, of models written. All of them have passed this test, these tests that predict the future for the past, at least. And then they choose the best ones of those. And then next year, when they get all those results back, they report what was bad, what was good. Some might have predicted that more heat went to the atmosphere, therefore the atmosphere should have been warmer by 0.2 degrees than it was, when in fact it actually went to the ocean. So they'll say, okay, well, what models got that part right? Because that seems to be more important. So they'll throw out the models that didn't do so good that year and pull in the new models that did better for this year, and then they report that too. So every year they come back and report what's good, what's bad, what's ugly, what's awesome, and they report exactly which ones they're getting rid of, exactly which ones they're keeping, exactly which ones they pick, and why they did so. And not only that, this has been used on other planets. Carl Sagan wrote one of the first global circulation models, but he wrote it for the planet Venus. And guess what? We got there and it was right. So it's absurd to think that global circulation models, i.e. global climate science, is not right. Now, what's not absurd is to try to decide how much are we going to do about it. Because to be honest with you, and I don't want to sound like a selfish jerk here, but this is the reality of it. America's the richest country in the world. We, in some sense, as a government, as a people, believe right, might makes right, and we are mostly going to be unaffected Not completely, by the way. We are mostly going to be unaffected. Our low-lying lands will disappear. Outer Banks, Virginia Beach, Louisiana, a good chunk of Florida, all that swampland in Georgia and Alabama and Mississippi, all that crap's going to be gone. It's going to be underwater. A lot of that's people's homes, and most of it is poor people's homes, but a lot of it's government land, and a lot of it's very, very wealthy people's homes. But we will survive, but we will also have increased diseases and stuff of that sort. So I just want to let you know, there are side effects to this that mostly affect the poor way, way more than they would us as the first world country. And we just discovered that now that oil got over $100 a barrel, we can finally make money on shale oil, which we've known for over a century. T-Bone Pickett said, you know, what's the good of that oil? It's not going to do a damn bit of good until we get, you know, oil over $100 a barrel, which at that time was around, you know, $10 a barrel or something like that. So he just never imagined it getting that. Well, guess what? It got that bad. When we went into Iraq, it got bad enough that we had barrels of oil for well over $100. That means shale became valuable. Now we've got more oil than any other country in the world. And we've got a lot of people that want to make that money. And for good reason. You know, if you can get rich, you probably are going to try to get rich. But the problem is we're going to do it at a cost. BP itself, their own scientists said, if we burn our reserves only, and I'm talking about BP's reserves, not United States, just BP reserves only, they will raise the climate of planet Earth by more than 2.5 degrees Celsius. Just them. 2 degrees Celsius is the goal that we try to set. We don't want to go any further than that, and they could do that with that alone. So read up on it all you want. There's a great series, Hot in My Backyard, HOT in My Backyard, on This American Life, where they talk to real scientists and real politicians about it. I highly recommend it. Check it out on NPR. But you guys are free to go. Thanks for coming, everybody. I'll stick around in case anybody have any questions. Thanks for staying. You actually stayed 5 minutes late to hear my cool story, so that's cool. Have a good one, everybody.
Have a good one, Professor.
You too.
Professor Younger,
Yes.
I just wanted to, I'm about to send you an email, but I wanted to talk to you about it real quick. For some reason, my unofficial TCC transcript is